Okay, welcome back to another rates video. We're making this in class, so if you hear some chatter, it's just my students. Number one, a ladder 25 foot long is leaning against the wall of a house, right? So let's draw a picture of this. Chances are we're going to have what type of a triangle? A right triangle. We're going to assume that the house and the ground are built perpendicular to each other. Okay, hopefully that was the builder's intention and we're not building on a steep slope. Okay, so what is not changing? The ladder, right? This is 25 feet. No matter what the ladder is doing, it is 25 feet. Okay, the base of the ladder is being pulled away at a rate of 2 feet per second. So the base is down here, right? Let's, since this is horizontal, let's call this X, and we'll call the vertical part Y. So which rate are we given in our problem? The X. So we're given dx dt. We know the rate that it is moving away is going to be 2 feet per second. And positive because the X value is growing, right? It's getting larger as it's moving away from the house. Okay, and consequently, according to physics, our ladder would be sliding down the house, right? So this is probably going to be a negative rate when we figure it out because it's moving down. Those y distances are getting smaller, so your rate will probably be negative. So let's see, how fast is the top of the ladder moving down the wall when the base is 7 feet? So we want dy dt, right? That's the top. We want to find dy dt when x equals 7. Okay, so here we're going to start. Now, what is the relationship between every right triangle when we know the hypotenuse? His name is Pythagoras, exactly. So x squared plus y squared equals 25 squared, which is 625. Which isn't really important because now we're going to implicitly differentiate both sides. So we differentiate with respect to time. So every variable gets a rate. Every variable gets a rate. So now let's see what we know. So we can do some substitution here. We know that x is going to be 7, right? So we'll put a 7 in here. Yes, this might be sloppy, but it's okay. We know dx dt is also 2. So 2 times 7 times 2, that's 28, right? So this whole entire thing will become a 28. Now, if we want to solve for dy dt, we're going to subtract the 28 to the other side, giving us an equation that looks more familiar like this. 2y dy dt equals negative 28. Okay, so there's one piece of information that I need to figure out real quick, and that is, what is the y value? Okay, so what is this y value? If we could figure that out, then we have our dy dt. We can divide both sides by that, and we will be done. So we're going to figure out the y value with our buddy Pythagoras again. Okay, so we know that y squared plus x is 7 squared equals 25 squared. Okay, so we go back to our original Pythagorean theorem in order to figure out what this y value is. And it looks like if we do this math, y will be 24. There's a special right triangle, right? The 7, 24, 25, that's a Pythagorean triple. If you have a calculator, that will tell you the same thing. So y is going to be 24. So now that we know our y value, we can continue with this problem. That's 24, not 2, by the way. Dy dt, and I probably should have gave myself some more space, huh? So this is 48. 2 times 24 is 48. So when I divide both sides by 48, negative 28 over 48, which can probably be simplified, divisible by 4 maybe? Negative 7 over 12. And our units are in feet per second. So negative 7/12 feet per second. So that is the rate at which the top of the ladder is sliding down the wall. Negative 7/12 feet per second. Okay, so we start with Pythagoras. We differentiate both sides with respect to time, plug in what we know, and then solve for the rate. Okay? So now part B says, consider the same triangle. Find the rate at which the area of the triangle is changing when the base of the ladder is 7 feet from the wall. Okay, so now we have an area. So think about the formula for the area of a triangle. Area is 1/2 of the base, which I called x, times the height, which I called y, right? Not b and h, but rather x and y for this particular picture. Okay, so let us go ahead and implicitly differentiate this thing with respect to time. So, area becomes dA dt, excellent, equals 1/2 is our constant, so we can pull that out. Okay, and now we have x times y. So this is going to be a product rule differentiation. Okay, I'm going to call my x my g, and the y, or the f is, anyway, that's what we got. So that if we're using the product rule, that's f prime times g plus f times g prime. Right, so that's how we use the product rule when we are multiplying two functions together. And since x and y are both functions of time, we have to use the product rule. So let's look at this one step at a time. What is the derivative of just x? dx dt. Okay, and then we have to multiply it by g, and g is the letter y. Okay, plus, now we have our f function, which is just x, times the derivative of y with respect to time, which is dy dt. Okay, so when we implicitly derive these things with respect to time, this is the formula that I get. 1/2 of dx dt times y plus x times dy dt. Okay, so do we know any of these things? I think we know all of them, in fact. Dx dt from up above was, is that 2? Yep, so dx dt is 2 times, what was the y value? I believe it was 24. Yes, the y value was 24 from up above. Let me check. Yep, y is 24. Plus the x was 7, and dy dt, that was over here. Dy dt was negative 7/12. Okay, so now this is just a matter of combining fractions and doing those kind of things. So I'm going to pause and do that for a second. There we go. 527/24, and our units are in square feet per second. Okay, so that's the rate at which the area is changing with respect to time. 527/24, a nice fraction. Okay, so the last one. Find the rate at which the angle formed by the ladder and the wall. The angle formed by the ladder and the wall. So let's see what this one looks like, if we can talk about the angle formed by the ladder and the wall. Okay, so that would be this angle up here. There's the angle between the ladder and the wall. The rate at which that angle in the wall is changing when the base of the ladder is 9 feet from the wall. So now we have our, we're looking for d theta dt, right? A rate at which the angle is changing when x equals 9. So not when x is 7, but when x equals 9. Okay, so I guess what they're giving us is the opposite side, and we, of course, have the hypotenuse is 25. So which trigonometry, which trig represents the opposite and the hypotenuse? That would be the sine. So we're going to write the formula. The sine of our angle equals the opposite side, which is x, right? X is the opposite side, over 25. X over 25. Okay, so here's our equation that we need to implicitly differentiate with respect to time. So let's look at what is the derivative of sine. That's the cosine of theta times d theta dt. Every variable needs a rate. So if theta is our variable, we have times d theta dt. Okay, now x over 25 is the same as 1 over 25 times x. So that's 1 over 25 times dx dt. And notice there's not an x in my equation anymore. So I don't really need to know when x is 9. That's not that important to my formula. Maybe it's important to something else, so let's see. We want d theta dt, so we can get rid of our cosine by dividing both sides by cosine. Right, so what if I multiply this by 1 over cosine? That's the same thing as dividing. So I have 1 over 25 times d theta dt. Do we know what dx dt is? I believe we do. Dx dt was 2, right? This was 2 feet per second. And 1 over the cosine. So is this a unit circle angle? It's not, is it? These are not unit circle things. So we're going to have to come over here and use our pre-cal and look at the ratio. So the cosine is a ratio of the y distance over the hypotenuse. Okay, so I guess as x is 9 and this is 25, we can figure out really quickly what our y value is. 25 squared minus 9 squared. 625 minus 81 is not a pretty number, is it? The square root of 544 is the length of y. So the cosine of my angle, according to pre-cal, is root 544 over 25. The adjacent side over the hypotenuse is my cosine. So over here I have the reciprocal of cosine, which is also known as the secant. So the secant is the hypotenuse over my adjacent side. 25 over 544, root 544. Okay, so 1 over the cosine is the reciprocal of our cosine, aka secant. So it's the radius over the y value. And now let's simplify. So my 25 on top cancels out with my 25 on bottom. That's handy. And I just have a 2 in my numerator and this wonderful root 544 in your denominator. And since this is calculus, you don't have to simplify that at all. But our rate, right, this is an angle, so I'm assuming these are going to be in radians per minute. Okay, so the angle is changing at a rate of 2 over root 544 radians per minute. Wow, that's some stuff right there. Okay, here we have an airplane flying right at constant altitude. So this is our ground right here. Let's draw the ground. I have a green here. This is our ground. Right, the airplane is up here in the sky somewhere 5 miles above the ground. Right, and we always measure height perpendicularly, exactly perpendicularly to the ground. Okay, so we're going to call this point down here our antenna. Okay, so it flew over some antenna. Okay, so the plane, let's say the plane is going this direction. Right there. There's our airplane flying in that direction. So we were asked for this. What is the distance between the antenna and the plane at a certain time? Okay, right? That is at the rate at which the distance between the plane and the antenna is changing. So we want d dt, right? The rate of the distance is changing. The distance is changing when what? When x is, then the plane is 10 miles past the antenna. When x is 10. Okay, and I'm calling that x because that is a horizontal distance traveled. So x is your horizontal axis and y is your vertical axis. Okay, and we're going to assume that this is 90 degrees here between the vertical and the horizontal. So we want the distance changing when x equals 10. Okay, so this looks like a perfect Pythagorean theorem problem. Perfect Pythagoras. Okay, a right triangle. So Pythagoras says 5 squared plus x squared equals the hypotenuse, which I'm calling d, the distance between the antenna and the plane, squared. Okay, so we start with Pythagoras. Most right triangles will have a Pythagorean theorem formula. Okay, so now let's differentiate with respect to time. What's the derivative of a constant? 0 plus x squared is 2x dx dt equals 2d dd dt's. Distance with respect to time. Okay, so let's see. What is the speed of the plane, right? What is that we're asked for? That is this. The speed of the plane is the rate at which our x value is changing. Okay, so we are trying to find dx dt. Okay, do we know what x is? Sure, x is 10, right? So this is 2 times 10. Do we know the distance? We don't know the distance, but we can Pythagorize to figure out what the distance is. Yes, 5 squared plus 10 squared equals d squared. So the distance is the square root of 125. That's 100 plus 25 is 125. Okay, so we know all this information. That's fantastic. Let's go ahead and put everything that we know in there. So 20 dx dt's, right? 2 times 10 is 20, equals 2 times root 125 times the dd dt, right? The distance, the rate the distance is changing, and that is 240. 240 is the rate that the distance is changing. So our dd dt is 240. So let's divide both sides by 20, and I think we're done. So 2 times 240 is 480. Root 125 over 20. Now, if this were an FRQ, calculus would give you that point, right? That is a completely awesome point, and I believe our rate is miles per hour. Okay, now since we're a little bit smarter, if this is a multiple choice, chances are we're going to have to simplify this. So 480 divided by 20, that is 24 roots of 125 miles per hour. I'm sure we can go further, but I really don't want to today. So that is a nice one. 24 roots of 125 is the rate at which the distance from the plane to the antenna is changing when x equals 10. Okay, so these next couple of problems really need you to remember your geometry from your sophomore year. So let's see how we do. Okay, suppose a 6-foot tall person is 10 feet away from a 10-foot tall lamppost. All right. The person is moving away at a rate of 3 feet per second. So here's our rate, the rate of something. So let's draw ourselves a picture, a nice picture. So here's the ground. There's the ground, perfectly level, horizontal ground. Okay, here's our lamp post. We're going to assume that the engineers put in our lamp post perpendicularly to the ground. Okay, our lamp post is 10 feet. Okay, and then there's a guy that's 6 feet tall, so we're just going to represent him with a straight line, vertical line here, 6 feet tall. And he is 10 feet away, and there's going to be a shadow, right? So if you remember your geometry, the light comes from the post and hits his head and casts a shadow out here in front of him. Oh, a person or her. I would not want to be gender specific. So this is your shadow out here. Right, that's your shadow there. And let's see, what else do we know? What else is changing about this situation? Right, our shadow is changing. What else is changing? Right, this is changing. The distance away from the lamppost is changing. So let's let this be x. And then the shadow is s. Okay? So if we're calling the distance from the lamppost to the person x, then our 3 represents dx dt, the rate at which the person is walking away from the lamppost. Okay, and since this distance is getting greater, it's going to be a positive value. So we're going to have a positive 3 as our rate, because the distance is increasing away from the lamppost. Okay, at what rate is the shadow changing? So our length of our shadow. So we're being asked for ds dt, the rate that the shadow is changing with respect to time. Okay. So from geometry, hopefully you remember this situation. Okay, we have a triangle inside of a triangle, right? These are nesting triangles. So we have this large triangle, okay, with a height of 10, and we have this smaller triangle with a height of 6. Okay, so these triangles, because they have two angles that are the same, right, they both share this angle and they both share the 90, that means these two triangles are in proportion. Okay, so we're going to solve this by writing a proportion. So let's see, where did our shadow go? To which triangle does our shadow belong? Right, that's this one, right? The shadow goes with the 6-foot tall person. So then how about the base length of our other triangle? Right, that's S, and what else is going on? Right, this is X. So the whole entire bottom side is X plus S, right? The distance he is away from the lamppost plus the length of the shadow. So we're going to set up a proportion in order to make our equation, right? So we're comparing like sides. So if I compare 10, what does 10 compare to? The vertical side here compares to 6, equals the long leg here, X plus 6, compares to just S. Okay, so here is our proportion that we're going to now, let's simplify this before we have to take the derivative, right? That's going to be a quotient rule on the right. So let's simplify. Cross multiply, that's how we solve these. Okay, cross multiply. We get 10s equals distribute 6x plus 6s. Okay, so then let's get our s's on the same side, so I will subtract that. 10 minus 6 is 4 s's equals 6 x's. So if we want to find s, let's divide both sides by 4 so that we can isolate our variable s. So the shadow is 3/2 as long as the distance the person is away from the lamppost. Okay, and that's a pretty simple ratio, and I am so happy because now we're going to differentiate both sides with respect to time and have a really simple equation. So we have ds dt, right, that's the derivative of s with respect to time, equals 3/2 times dx dt. Okay, and from before, I believe dx dt was 3. So ds dt equals 3/2 times 3, which is 9/2. And our units are feet per second. 9 halves, so 4.5 feet per second. Okay, that's the rate at which the shadow is increasing. Notice it doesn't really depend upon how far the person is away from the lamppost. Right? That x equals 10 did not even come into play at all in our problem. Okay, so let's see, what else does it say? At what rate is the tip of the shadow changing? Okay, so how is the tip of the shadow different from the exact shadow? Okay, that's a tricky question. So the tip of the shadow is referring to this whole entire length down here. Right, the tip of the shadow is here at the very, very end of our triangle. Okay, so that is just x plus s. Right, the x plus the s is the length of that whole entire bottom side down there. So let's differentiate with respect to time each of those things, shall we? And we have dx dt plus ds dt. So our shadow is changing at the sum of our two rates, which makes perfectly good sense. Okay? If this much is changing at a certain rate, and this much is changing at a certain rate, then the whole entire thing is changing at the sum of those two rates. Okay, so dx dt was 3, and ds dt was 9/2 or 4.5. So the shadow is changing at a rate of 7.5 feet per second, right? The whole entire length of that side of our triangle is changing at this rate. Okay, so it's not like we have to do any more calculus. We simply have to recognize that the tip of the shadow represents the entire bottom length of that triangle. And that is the sum of those two things. Okay, so whenever we have a nested triangle, right, a triangle inside of a triangle, you're going to be using some type of a proportion, okay, a proportional relationship to set up your equation. Okay, and that's what we're going to do on number 4, the cone problem. So these are wonderful. We did a lot of them in geometry. A cone has a diameter of 10 and a height of 15. Okay, so if the diameter is 10, that means the radius is 5. So a maximum radius of 5 and a maximum height of 15 if the whole entire thing is full, right? So if our cone is full, then the radius is 5 and the height is 15. Okay, chances are it's not full. Water is being poured into the cone so that the height is changing at 1.2 inches per second. So that's dh dt, right? The height is changing, so dh dt equals 1.2 inches per second. The height is changing. At the instant when the radius is 2 inches, so when radius is 2, at what rate is the volume of the water changing? So we want dv dt is equal to what when r equals 2? When radius equals 2, how is our volume changing? Okay, so we start with the volume formula for a cone. And hopefully this will be given to you in your calculus questions. So the volume of a cone is 4/3. No, it's not 4/3. That's a sphere. I digress. It's 1/3. 1/3 pi r squared h. Okay, it's 1/3 of a cylinder. Oh, my brain. Okay, 1/3 of pi r squared h. That was a sphere formula for a second ago. This is a cone formula. So how many variables are in our cone formula? Too many is what's going on. Too many, right? We only have the rate of one of them. We have the rate of the height, which means we want to have an equation with just the height. So somehow we have to find a relationship to replace our radius with, right? So we can just have one variable in terms of h, the height. Okay? So hopefully from the last question, what do we notice about these triangles here in our cone? Right? They're nested, so they're proportional. If we compare the radius to the height, okay, that's the same as saying 5/15. Right? The radius is always 5/15. So this is any given radius and any given height has a ratio of 5:15. Okay? So if we solve this for r, right, we cross multiply. 15r equals 5h. That means one radius is h/3. The radius is 1/3 of the height. Okay, which makes sense, right? When the height is 15, the radius is 5. So the radius is 1/3 of the height. So I'm going to put that right here, h/3, into my volume formula. Pi, we're squaring that, timesing it by h, 1/3 equals volume. Okay, so when we do this algebraic simplification, we get pi h cubed over 27 as the volume formula for this particular cone where the radius is 1/3 of the height. Okay, so that's our formula. Now let's differentiate with respect to time. So we have dv dt equals 1/27, or rather pi over 27. right? Pi over 27, because those are our constants. And then we have h cubed, which is 3h squared times dh dt. Okay, so this is our derivative implicitly with respect to time. Pi over 27, 3h squared times dh dt. Okay, so let's plug in everything that we know right now. Pi over 27 doesn't change. I guess we could do the 3, right? This could reduce here, and I can make the denominator now a 9. I guess that would make it a little bit easier. Okay, 3 on top, 27 on the bottom. That reduces to 1 over 9. I'm going to have to probably figure out what the height is, aren't I? I don't know the height, but I know the rate is 1.2. Right? The rate at which the height is changing is 1.2. So when my radius is 2, okay, if the radius is the height divided by 3, and my radius is 2, then what is my corresponding height? 6. So the height is 3 times the radius if the radius is 1/3 of the height. So I can plug that in here. That's now a 6 squared. Okay, I think I have everything that I need. So let's get to doing this math. Okay, 6 squared, that's 36. Yes, 36 is 6 squared. Would you all agree? 36 divided by 9, that's 4 pi times 1.2. So 4 times 1.2, let's see, let's do that and leave it with pi. So that's 4.8 pi. Let's see what our units are. Inches, so this is volume. So cubic inches per second. Wow, that seems like a lot. But who am I to judge? So the rate of the volume is increasing at a rate of, the volume increasing. And the volume is increasing at a rate of 4.8 pi cubic inches per second. Okay, that's probably the most intense one that we're ever going to do. Okay, is one of those guys. But remember our geometry. Whenever we have a triangle inside of a triangle, you have a proportional relationship. And then in Pythagoras, anytime we have right triangles. And don't forget about your trig from pre-cal. That's a lot. Have a great afternoon.